continuing our conversation about the partition generating function, which is p of x. By definition, it counts integer partitions in a ordinary generating function, and we found that it's equal to the product of all I greater than equal to 1, of 1 over 1 minus x to the I. So this is an infinite product, which is kind of tricky to work with. Let's think about a variation of this. Here we have p less than or equal to kn. This is going to be the number of partitions of n with at most k parts. So now I'm bounding the number of parts. Let's see how we can use this formula to get a generating function for this. First, it always helps to do an example. So let's do an example, a sub-example, I suppose, of this example. And let's do it for n equals 6. And let's count how many integer partitions there are of 6 into, let's say, k equals 3. So we're doing partitions that are going to be of the form lambda 1, or lambda 1, lambda 2, or lambda 1, lambda 2, lambda 3. And of course, the sum of the lambdas in any of those cases has to be 6. So in this case, we could just take a single part of size 6. That's perfectly legitimate. If we're going to have two parts, how can we do that? Well, we can have a 5 and a 1, or we could have a 4 and a 2. That's it for having, or we could have a 3 and a 3. That's it for having two parts, right? It's going to be these three cases. What if we ended up wanting to have 3 parts? Okay, now we can do a 4, 1, and a 1, or a 3, a 2, and a 1, or 3 2s. And that's it, and we get a total of 7. So there are 7 integer partitions of 6 into 3 parts, and here they all are. But remember, the way our partition generating function worked is we were counting whatever coefficient we took from this part of the infinite series. That was telling us how many parts we had that were equal to that. So let's remember what that said. What we had said before, say we can scoot these guys all over a little bit. What we had said before, remember that 1 over 1 minus x to the I, whatever term we take from this expansion, remember that when we write it out, we get this. This is telling us how many parts, so this would correspond to take 2 parts of size I. That would contribute a total of 2 to the I, to the exponent, which is correct because that's how many we'd be contributing to the partition. So how do we interpret this using this idea? So here we're bounding the number of parts, and we're not saying anything about their size. So it might look like we can't really do it, but in fact, we can. So remember that beautiful operation that we had called conjugation. What does conjugation do? And this is one of the big reasons why we draw integer partitions or represent them graphically. So if we were to take a partition, for example, 4, 3, 1, so that would mean 4, 3, 1. What is the conjugate of this partition? To conjugate, we draw a line around the main diagonal and we reflect. So what is that going to do? Well, to each of these guys, what it's going to do is flip it like this. And now we can see, okay, well, let's flip it. This one stayed the same. Let's flip it. Let's flip it. Flip it, flip it, and flip it. Now what's happened? If you look at the partitions, they've gotten tall and they're not very wide. So what does that mean? So let's interpret this condition of the number of parts. So if the number of parts of lambda is less than or equal to k, that means that we have lambda 1 all the way up to lambda j, and we know that j is less than or equal to k. That's what this is counting. The number of partitions that don't have too many parts. Well, what's j in this picture? In this picture, j is equal to 3. What happens when we conjugate the partition? When we conjugate the partition, we change the height for width. Now we have the partition 3, 2, 2, 1. So again, we've just flipped across this main diagonal. So that is what happens over here. So what has happened to this idea of having 3 parts? Here is 3, it now manifests into having the 3 right here. But what's this 3 over here? What's the interpretation here? These are all partitions where lambda 1 is less than or equal to 3. But that implies that lambda I is less than or equal to 3 for all I. Why? Because the parts get weakly smaller. So if I'm bounding this, instead of bounding the height, I'm bounding the width. Now we can use this interpretation and this generating function to come up with a generating function for these partitions. This generating function is the same as if I thought about the generating function of all partitions where the parts, the size of the biggest part is at most k. Well, keep in mind that you're taking one term from here whenever you have a part of size I. So this means that what I actually get is a beautiful finite product. I equals 1 to k of 1 over 1 minus x to the I. And again, the reason comes down to conjugation, because really here I'm saying the biggest part is less than or equal to k. That's another way to interpret the number of parts. So using this interpretation that we get under conjugation gives us a really powerful tool whenever we're dealing with something where we care about how many pieces we're breaking a partition into.